Hi. This presentation concludes our approach to Chapter 1 of the book called Fundamentals of Computer Design and Analysis. After watching this presentation and completing the learning task proposed at the end, you should have achieved these specific learning outcomes related to the semantics of common expressions, the importance of technology for computing performance, and energy efficiency aspects. The book that we are following assumes that computer implementation is an activity comprising two main components. Organization, which is related to higher level decisions, and hardware, which represents the lower level design tasks such as detailed logic design. When we speak about computer architecture, on the other hand, we are also considering instruction set design besides organization and hardware. Technological developments over the years have had a profound impact in computer design. Billions of transistors per chip are now available from multiple vendors. Dynamic random access memory devices go up to 16 gigabits. And there's a wide availability of flash memory that is 8 to 10 times cheaper than per bit than DRAM. Magnetic disk technology, on the other hand, is even cheaper, and network technologies have seen great improvements. So these developments have a great impact on performance, which combines bandwidth, which is particularly important for servers and warehouse-scale computers, and latency, which is more important for embedded applications, computers addressing real-time applications. Performance improved greatly over the years, but technology-driven improvements are now far more limited. Feature size, which is a distinctive feature of semiconductor device fabrication, probably won't get below 7 nanometers. And it's a huge progress since 1971, but that's about it for the feature size cycle. And the number of transistors per chip no longer doubles every few years, as Murphy predicted. Neither does the power density continue to be constant for a given area of silicon, independently of the number of transistors, which was Dinard scaling. It is interesting, nevertheless, to look into the performance milestones over the last 25 years. I'm not going through each line shown here, but please look at what happened since 1972 concerning the number of transistors per chip, the total number of pins, or the bandwidth in millions of instructions per second. What you see in this slide is actually just part of the complete table that is presented in page 22 of the book, where you can also find data concerning memory modules and local area network and hard disk technologies. So power consumption is now the main challenge faced by computer designers. Please bear in mind that power is the total amount of energy per time unit. The Intel Core i7-6700K consumes nearly 100 watt, but the more recent Xeon microprocessors have a thermal power rating that is even higher, up to 165 watts. There are four main techniques to improve energy efficiency, and the first one being to turn off the clock of modules that are not being used at any given time. A second technique called dynamic voltage frequency scaling reduces voltage or clock speed during low activity periods. And a third technique assumes that devices will not always operate under worst-case conditions, and so we can rely on emergency shutdown features to prevent problems. And finally, microprocessors are now commonly support an overclocking mode that increases the clock by about 10% during certain periods. Now this slide shows the relative energy and area costs of various common building blocks. Notice that a 32-bit floating point addition takes 30 times more silicon area than a simple 8-bit addition. But this difference is even higher if we look into their relative areas. Yet this is so much lower than the difference between the energy consumed by a 32-bit DRAM read access cycle and the same 8-bit addition considered earlier. So it's a struggle to search for the best trade-off between performance and energy consumption. The technology limitations that we've looked into were behind the decision of Intel to abandon the high-performance uniprocessor paradigm in 2004, when it became clear that multiple processors per chip were the way to go. Murphy's Law and Dinard scaling are no longer valid, but there's another law that is not likely to disappear. Amdahl's law says that if 10% of any given task has to be executed serially, then the maximum performance benefit from parallelism is 10, no matter how many cores you put on the chip. Actually, Amdahl's law applies to other domains as well, such as reliability. So parallelism is important, but it has its limitations as well. I'll leave you now with this recommended learning task. Look into Wikipedias for CPU power dissipation and explain this statement found there according to Amdahl's law. So use Amdahl's law to explain this statement. Thanks for your attention.